We will discuss Shannon's sampling theorem, which is the analytical approach of determining the sampling theorem, or understanding why omega s must be greater than 2 omega 1 for the sampling process. Right. So we will see under this, when we are going for Shannon's sampling theorem, we should first find out or try and recap the Fourier transforms. The Fourier transform of f of xt, Fourier transform of x of t, where x of t is any continuous time signal which is existing from minus infinity to infinity. You can say that this is x of j omega. The Fourier transform of x of t, you will be having x of j omega, which is nothing but integral over minus infinity to infinity e power minus j omega t x of t dt. Right, and the inverse Fourier transform of x of j omega, we will be getting back the continuous time signal x of t, which is nothing but 1 by 2 pi integral over minus infinity over infinity e power j omega t x of j omega d omega. So this is what we are trying to see in this case. Now let us say, when a continuous time signal x of t, when it is applied to over a sampler, you are getting x star of t. Now what is this sampler? It is train of impulses. As we have discussed in our impulse sampling lecture, train of impulses are nothing but the magnitude of impulses which are equal to 1 unit train of impulses, right? And this exists from k is equal to 0, 1, 2, 3, 4, so on, which is k. And if this signal x of t is any sort of signal, then x star of t is the product of, you can say, you will have values at every instant, at k is equal to 0, k is equal to 1. So that values, you are calling it as an infinite sum, or you can say it is x of 0 del t, or you can call this as del of t, and plus x of t at this instant 1 into the value at this point, that is x of t. Therefore this is del of t minus t plus x of 2t del of t minus 2t plus so on. And also you are having x of minus t del of t plus t, plus the backward, if you are going, you have unit impulses on the negative side also. When you are treating this as a periodic signal, x of t is a periodic signal which is existing from minus infinity to infinity, then you can say that it is having values on both sides of the 0. Therefore you are having this. Therefore, how can we represent x star of t? X star of t can be represented as sigma as k minus infinity to infinity x of kt. You can add x of minus t, x of 0, x of t. Generalizing these things, you can say del of t minus kt. Therefore, x star of t is del of t minus kt. Now when I am trying to find the Fourier transform of x star of t, when we are trying to find the Fourier transform of x star of t, what is this Fourier transform of x star of t? We have x star of j omega, which is nothing but equal to minus infinity to infinity. As per this equation, you have e power minus j omega t x star of t dt. Now when I replace this equation 1 in equation 2, substitute equation 1 and equation 2, I have x star of j omega is equal to integral over minus infinity to infinity minus j omega t. And what is x star of t? It is sigma over sigma k minus infinity to infinity x of kt del of t minus kt, and this is over this and into dt. So after simplifying this equation, we can say that x star of j omega is equal to integral over minus infinity to infinity. You can say here e power minus j omega t sigma k minus infinity x of kt del of. Where integration and summation both can be interchanged without any loss of generality. You can say that x of kt, it is always of this form, so integral can be removed from this, and you can say that k minus infinity to infinity, you can say x of kt. If I can replace this, now e power minus j omega t, it is a continuous time exponential decayed function, and if it is multiplied with del of t minus kt, which is train of unit impulses, then you can say e power minus j omega kt. Now integral over e power minus j omega t sigma over del of t minus kt and dt. All this combinedly you can put it as e power minus j omega kt sigma from k is minus infinity to infinity. So without any loss of generality, you can convert this equation into this form. Now with this in mind, now we will see what is x star of j omega, which is nothing but when you have dealt with impulse sampling, we have that x star of j omega is equal to k 1 by t sigma k is minus infinity to infinity x of kt x of j omega plus j omega s k. Now this is the equation. By definition, you are getting x star of j omega is equal to 1 by t sigma. You can say that it is existing from minus infinity, for example, and 1 by t x of j omega minus j omega k into 1 plus 1 by t x of j omega when k is equal to 0. This is when k is equal to minus 1. This is when k is equal to 0 plus 1 by t x of j omega plus j omega s plus this is when k is equal to 1 plus so on. Therefore, it is existing from minus infinity to infinity. Now let us say here we are considering x of j omega. We are considering x of j omega is equal to 0 for omega greater than omega 1 and omega less than minus omega 1. That is, I will try to once again replenish this frequency spectrum of our function minus omega, and this is minus omega 1 and omega 1, and this is mod x of j omega. Right. Let us assume that x of j omega is equal to 0 for all omega greater than omega 1 and omega less than. That is, x of j omega magnitude is for all omega greater than omega 1, this region x of j omega is 0, and for omega greater than minus omega less than minus omega 1, x of j omega is equal to 0. With this in mind, you can say that these are the things. So you can say now this is a function or a frequency spectra which is going to 0, and this is a frequency spectra which is going to 0. Therefore, what is x star of j omega from this function? X star of j omega is equal to 1 by t x of j omega. When when omega greater than omega 1 and omega less than minus omega 1. So this is the condition. Under this condition, x star of j omega is equal to 1 by t x of j omega. Now you can see from this diagram, from this equation, you can say that x star of j omega is uniquely determined by x of kt. You can say x star of j omega is uniquely determined by x of kt. Now this is the point that we are going to discuss in Shannon sampling theorem, right? So x star of j omega is a frequency domain function, and x of kt is a sample data signal, and x star of j omega can be obtained by the values of x of kt when you are going with this formula. That is what we are trying to see. So x star of j omega is uniquely determined by x of kt, and with this in mind, after getting this, what we are trying to see is we are having x star of j omega is equal to 1 by t x of j omega when this frequency spectrum is considered and when the conditions are given like this, when omega is greater than omega 1 and omega is less than minus omega 1. Now considering this in mind, you can also say that now for sampling theorem to exist, for sampling theorem we require omega s greater than 2 omega 1. For sampling theorem to hold good, we require omega s greater than 2 omega 1. So I can write omega s by 2 here and omega s by 2 here. This is minus omega s by 2 and omega s by 2. Now without any loss of generality, you can also say that the same x of j omega is equal to 0 when omega is greater than omega s by 2 and omega less than minus omega s by 2. Now we are considering this sampling frequency, half of sampling frequency on both sides, so that we know the value of omega s here, which is 2 pi by t. And the highest frequency component omega 1, we are considering omega s greater than 2 omega 1. With this condition, and omega s is equal to 2 pi by t, because we know the value of omega s here, therefore you can say that x of j omega is equal to 0 for all omega greater than omega s by 2 and omega less than omega s by 2. That is, from this frequency spectrum of x of j omega, you can understand that there is no value of x of j omega beyond minus omega s by 2 and beyond omega s by 2. The x of j omega is equal to 0. So with this in mind, you can go with this transfer function, this equation, and this equation can be modified here with x star of j omega is equal to 1 by t x of j omega when omega is greater than omega s by 2 and omega is less than minus omega s by 2. So this is the modified and finalized condition for x star of j omega is equal to 1 by t into x of j omega. So with this in mind, now I want to reconstruct back the original signal by using inverse Fourier transform. Therefore, I need x of t by using inverse Fourier transform. Inverse Fourier transform, I will have 1 by 2 pi integral over minus infinity over infinity e power j omega t x of j omega, or I have x star of j omega d omega. I have the values of x star of j omega. X of j omega, right? X of t. If it is x star of t, you will have x star of j omega. I want x of t because I doesn't want the sample data signal, I want the continuous time signal back, therefore x of t, I will have x of j omega here. And what is x of j omega here? X of j omega is equal to t into x star of j omega. So for I can replace that here, which is here 1 by 2 pi, and what is the condition here? Omega greater than minus omega s by 2, omega less than, and omega greater than omega s by 2, with this into condition. Now when you are having d omega here and the omega values are varying from minus infinity to infinity, I can put it here like minus omega s by 2 to omega s by 2 e power j omega t. What is x of j omega? It is t into x star of j omega d omega. Which is nothing but 1 by 2 pi integral over minus omega s by 2, and t can be taken out. It can be written as t by 2 pi minus omega s by 2 to omega s by 2 e power j omega t, and x star of j omega d omega. And we know that omega s is equal to 2 pi by t, and therefore 2 by pi, t by 2 pi, it is 1 by omega s integral over minus omega s by 2 to omega s by 2 e power j omega t x star of j omega d omega. Now what is x star of j omega for us? In the previous case which we have discussed, which is nothing but sigma k 0 minus infinity to infinity x of kt into del of t minus kt. X star of j omega, it is sigma k is minus infinity to infinity